Hey guys, you did a great job learning how to draw regular, easy, simple Lewis dot diagrams last week. And now we're going to take a look at how to determine the best structure for more confusing or complicated molecules. So in order to do that, the first thing we have to learn about is something called formal charge. Formal charge is simply a method for determining the best structure. And what I mean by the best structure is the one that's the most representative of what the molecule actually looks like at the atomic level. So best structure or most representative. Now this is only going to come into play when you have options for what your potential Lewis dot structure could be. So based on those rules that we learned for drawing Lewis dot diagrams, sometimes you will arrive at this place or with an option, whoopsies, for more than one way to draw the structure. And so the question is, which of those structures is best or most representative of that particular molecule? So let's do an example and calculate formal charge as we go. I keep making these random lines. Okay, so the first thing we need is the equation for calculating formal charge. Formal charge is something that we will calculate on each individual atom. Okay, so calculated on each atom in the structure. Now, like I didn't leave myself enough room up here, I didn't leave you guys a ton of room either for this, so make sure you're writing small. Okay, and it might not make a lot of sense until we do a few examples, so don't worry about the equation. It'll make sense as soon as we practice it. Okay, so here's the equation for calculating formal charge. Formal charge is equal to the normal number of valence electrons on the atom minus the bonds plus the lone electrons assigned to that atom in the structure. Again, this will make sense as soon as we practice. Let's do an example. Let's draw the Lewis dot diagram for carbon dioxide. Normal rules. Count up your total number of valence electrons. 4 for carbon plus 6 for oxygen times the 2 in the structure is 12 plus 4, 16 electrons. Divide by 2. I'm working with 8 pairs of electrons. All right, so I'm going to put carbon in the middle because it's the least electronegative, and I'm going to connect it to an oxygen. I'm going to connect it to an oxygen. Of my 8 pairs, I now have 6 pairs remaining. The rules say to put those remaining pairs on the terminal atoms first. So there's 3, 4, 5, 6. I'm all out of pairs. Check to see that everybody is satisfied. Looking at this oxygen, 2, 4, 6, 8. Both of my terminal oxygens are satisfied, but my central carbon is not. So I'm going to erase one of those lone pairs, and instead I'm going to draw it as a shared pair. Now, if you recall when we did this example last week, you actually have a choice here. We could make a double bond on the left-hand side, right? We could erase one of these lone pairs and instead draw it as a shared pair. And then carbon is satisfied in the center with 2, 4, 6, 8. However, we could have, so over here on the right-hand side of your page, we could have done this. Like, let's say we were at this point with our double bond over here and our single bond on the left. This is where we were before we decided to do that other double bond. Instead of double bonding here on the left, I had the option to also erase a lone pair and make a triple bond on the right. So look, I don't like how that looks. I feel like it's like my triple bond is humongous and my oxygen's too far away. Let's make it pretty. 1, 2, 3. Oxygen, lone pair. Okay, that's better. All right, so now the question is, which structure is better? This structure here with a double bond on the left and the right, or this structure over here with the triple bond on the right and the single bond on the left? Now, by better, I mean, does the carbon dioxide molecule have two identical double bond lengths? Or does it have a very short triple bond and a very long single bond? Like one of these two things is actually representative of what carbon dioxide does at the molecular level. Now, of course, we're not able to see that very easily without an electron microscope. So we need a method for determining which structure is better. And that method is this formal charge calculation that we are about to do. So let's do the formal charge calculations for this molecule here on the right, the triple bond option. Now, normal number of valence electrons. So let's look at this oxygen on the left-hand side here. Oxygen normally has 6 valence electrons. So I'm going to take those 6 valence electrons and I'm going to subtract from that the number of bonds and lone electrons on this oxygen. So in my head, I'm going to go 6 minus the 1 bond. So 6 minus 1. And then all of these lone electrons, 2, 3, 4, 5, 6, 7. Okay, so I was doing 6 valence electrons minus the 1 single bond plus all 6 of those lone electrons. So 6 minus 7 is -1. So the oxygen here on the left has a -1 formal charge. Again, this is just a method that is going to, as soon as we're done calculating all of them, help us determine which structure is correct. All right, so now let's calculate the formal charge on the carbon that's in the middle. How many valence electrons does carbon have? Carbon has 4 valence electrons minus the bonds, 1, 2, 3, 4, and any lone electrons, which there are none, on that carbon. So 4 minus 4 is 0. So carbon has 0 formal charge. Let's calculate the formal charge for the oxygen on the right. First things first is the normal number of valence electrons that oxygen has, which is 6, minus the bonds, which are on that oxygen, 3, plus lone electrons, 1, 2. So not pairs of electrons, actual total number of electrons. So 6 minus 5 is a +1. Okay. Now, one of the ways to check yourself to see if you've done the correct calculations is if this molecule is neutral, in other words, if it's not a polyatomic ion with charge, the formal charge should add up to 0. And so you can see +1 and -1, yep, it adds up to 0. If it's a polyatomic ion, it's going to add up to the total charge on the ion. So I can see that we correctly calculated formal charge here. Now, it still hasn't told us anything yet. Let's calculate the formal charge on my other option, on my carbon dioxide with my double bond. Let's start here with the oxygen on the left. Normal number of valence electrons is 6 minus 1, 2, 3, 4, 5, 6. 6 minus 6 is 0. Carbon has 4 valence electrons minus 1, 2, 3, 4. Oxygen has 6 valence electrons minus 1, 2, 3, 4, 5, 6. Basically, it's just your normal number of valence electrons minus the things that are drawn on that atom in the structure. Okay, so now we need a few rules for determining which is better, this one or that one. Here are the rules for formal charge. The rules state that less formal charge is better. You know what? Instead of saying less formal charge is better, maybe fewer atoms with formal charge. The fewer atoms in your structure that have formal charge, the better. So then that answers our question. We don't even need any more rules, although there are more rules. Which of these is a better diagram? The one with no formal charge. This double bond option is the more representative molecule of carbon dioxide, or drawing of the carbon dioxide molecule. If we were to look at carbon dioxide with an electron microscope, we would see two oxygen atoms equidistant away from the carbon, as opposed to this other molecule, which would have shown one of the oxygens much closer to the carbon than the other. But it's not always so simple. So sometimes you have to have formal charge. So for example, in a polyatomic ion, you have to have formal charge, as long as the magnitude is not greater than 1. Okay, so a formal charge of plus or minus 2 is not okay. Oops. Plus or minus 2 is not acceptable. So if you get a structure that has that, you know that's the wrong structure. And then our final rule is if you have to have formal charge, you want the negative formal charge on the more electronegative atom in the molecule. So we'll see some of these rules come into play with a few more examples here. Okay, so it's just a method that we use to calculate on each individual atom in the structure to help us determine what is the more representative drawing of that molecule. We'll do some more of this as we talk about resonance. Okay, so I'm going to scroll down and let's talk resonance. I'm not going to define resonance until we do an example. I think it's better to do an example first. Okay, let's draw the nitrate, NO3 1-. Let's draw the nitrate polyatomic ion. All right, normal rules. Count up your total number of valence electrons. 5 plus 6 times 3. Don't forget about this negative charge here. That means you gained an extra electron. So we've got 24 electrons total. We're going to divide by 2. We're working with 12 pairs. Nitrogen is going to go in the middle. And we're going to connect that nitrogen to 3 oxygens. Of my 12 pairs, I now have 9 pairs remaining. My rules say to put those remaining pairs on your terminal atoms first, on your oxygens. 1, 2, 3. 3, 4, 5, 6, 7, 8, 9. I'm all out of pairs. Check to see that everybody's satisfied. It's quite clear to me that my nitrogen in the middle is not, right? All of my oxygens have 2, 4, 6, 8, but nitrogen's got 2, 4, 6. So I need to make a double bond. Now I've come across a choice. Where am I going to make that double bond? Well, I'm just going to do it here on the rightmost oxygen. Maybe you decided to do it on the leftmost oxygen. Maybe you decided to do it on the bottom oxygen. Guess what? It's not going to matter. Don't forget your last step of putting it in brackets with the charge on the outside because it's a polyatomic ion. Let's calculate formal charge and see if this is an acceptable structure. So, normal number of valence electrons on nitrogen is 5 valence electrons minus 1, 2, 3, 4. 5 minus 4 is a positive 1. Oxygen has 6 valence electrons minus 1, 2, 3, 4, 5, 6. This oxygen, normal number of valence electrons is 6 minus 1, 2, 3, 4, 5, 6, 7. And this oxygen looks the same as that oxygen, so it's going to have a -1, but we could calculate it. 6 minus 1, 2, 3, 4, 5, 6, 7. -1. Do you see how all of my formal charges add up to the charge on the polyatomic ion? So that means I calculated correctly. The next rule says that, less formal charge is better. So you might ask yourself, maybe if you guys drew your double bond down on the bottom oxygen, you probably had the same formal charge that I did. It's just which oxygen had the 0 formal charge. The one you double bonded has the 0 formal charge, but you don't have any fewer atoms with formal charge. And we don't have a magnitude of 2 or more. And the negative charge is on the more electronegative atom, which is oxygen. So this is an okay structure. But so was whatever structure you chose to draw. Like perhaps if you drew the double bond on the bottom oxygen, let's draw that. Everybody draw it with me. If this was where your double bond was, and then you had single bonds on the other side, that structure has the same formal charge arrangement, just in different places. But it has the same magnitude of formal charge. That means that these drawings are equivalent in nature. So like, here's your -1, here's your 0, here's your -1, here's your +1. And you're like, whoa, Mr. Vera, what if I had drawn my double bond on the other side? If you're tired of drawing, too bad. Keep drawing. You have to draw all 3 options, and not just because I said so. Once we're done drawing, I will explain to you why. Okay, my brackets and my charge. And finally, my formal charge. 0, +1, -1, -1. Here's the deal. The reason why we had to draw all 3 structures is because it turns out that when I look at this molecule at the molecular level, it does not have 1 double bond length and 2 single bond lengths. It turns out that that shared pair in the double bond spends equal amounts of time between each of the 3 oxygens. Remember, electrons are moving, right? In fact, what's going on in this molecule is that double bond, that double bond is spread out or delocalized over 3 locations. You could think about those electrons as resonating between 3 locations. And because I can't show a dynamic system with this static drawing, I have to draw all 3 options. And I draw arrows in between them to indicate the dynamic nature of that bond and the fact that it's distributed over 3 locations. So in fact, if I look at this molecule at the molecular level, all 3 bonds are the same bond length. And they're somewhere in between the length of a single bond and a double bond. It's like a bond and a third, right? Instead of a single bond, instead of a double bond, it's a bond and a third because that one bond has been divided over 3 locations. All right. That's what resonance is, you guys. Resonance is when more than one equivalent, and by equivalent, I mean same formal charge, more than one equivalent Lewis structure exists. When double or triple bonds are delocalized, that means spread out, over more than one location. In other words, in this NO3 1- molecule, there are 3 identical bond and a third bonds. Because this double bond, that pair of electrons, this shared pair that I'm circling right here, that shared pair is actually spending equal amounts of time here, here, and there. That's what resonance is. Okay, we're almost done. Hang in there. Some exceptions to the octet rule. Let's do 2 examples. So I'm going to do one on the left here, and I'm going to do one on the right. Oops, yep, that's good enough. Okay, let's draw BH3, boron trihydride. Boron has 3 valence electrons. Hydrogen has 1 times 3. So that's a total of 6. Divide by 2. 3 pairs. Put boron in the middle. Hydrogen can never go central, right? And our hydrogens will be terminal. I've used up all 3 of my pairs. And I'm all out of electrons. Here is where you would normally look to see if you could make double or triple bonds as necessary. But you have no lone electrons to do that with. So you're all out of luck. And you're like, oh no, boron isn't satisfied. Well, let's check formal charge and see if that's okay. Boron, normal number of valence electrons is 3 minus 1, 2, 3. No formal charge on boron. Hydrogen has 1 valence electron, 1 single bond, nothing on the hydrogen, nothing on the hydrogen, nothing on the hydrogen. This is an acceptable structure. This is called a sub-octet. So sometimes some of the smaller elements like boron, they can have less than an octet. We know hydrogen is always happy with a duet. That's not really an exception. But to have a central atom without 8 valence electrons is unusual, but it does occur. And that's when you have less than 8 valence electrons, and we call it a sub-octet. Let's do one more example. Let's do SF6. Sulfur, 6 valence electrons. Fluorine has 7 times 6. Oh, these are big numbers. 7 times 6 is 42, I hope. Plus 6 is 48. Divide by 2. Talking about 24 pairs of electrons. That's a lot of electrons. Sulfur is going to go in the middle as less electronegative than fluorine. And now I need to connect it to 6 fluorines. And you're like, wait a second, we've only had 4 bonds before. Well, guess what? Sometimes you can have more than an octet. So there are my 6 bonds to my fluorines. Fluorine, 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 fluorine. Are you tired of me saying it? Fluorine and fluorine. So of my 24 pairs, I have used up 6 of them. So that means I have 18 pairs remaining. How lucky that I've got 6 of these terminal atoms, 3 electrons or 3 pairs of electrons apiece, will be 18. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, oh, that was ugly, 15, 16, 17, 18. Oof, I'm all out of electrons. All right, let's check formal charge and see if that's an okay structure, even though I'm expanding the octet of the central sulfur. Sulfur has 6 valence electrons minus 1, 2, 3, 4, 5, 6. And fluorine has 7 valence electrons minus 1, 2, 3, 4, 5, 6, 7. So all of my fluorines are going to have no formal charge. There's no formal charge anywhere on this structure. It's a totally acceptable structure. This is called an expanded octet. Now, we can only expand octets when the central atom is in the third period or beyond. Okay? Let's think about why that might be the case. While I write that down, I want you to think about why that might be. When the central atom is in the third period or beyond. Think electron configurations, you guys, right? Like, why is hydrogen satisfied with just 2 valence electrons? Hydrogen is satisfied with a duet because hydrogen's in the first period, and the first period is full with 2 valence electrons. And then most atoms are satisfied with 8 valence electrons. So everything outside of that first period, which only has hydrogen and helium. So all of the other elements are satisfied with 8. That's because in the second period, you also have a p orbital available for bonding, right? So your valence electrons from the second period and beyond, valence electrons are now 8 valence electrons. So this is why hydrogen is satisfied with a duet versus most atoms that are satisfied with an octet. Once you get to the third period, yes, it's true that the third period contains only 3s2 and 3p6. However, even though in the third period they do not have any electrons in the d block, the third principal energy level is where d orbitals start to appear. So once you're in that third energy level, you now have a d block or d orbitals to put in more than 8 electrons. So more electrons can drop into this orbital on that central atom. And so that's why, in order to have an expanded octet, you have to have a central atom that has the potential to drop in electrons into a 3d or a 4d or a 5d orbital. Okay, you guys. Now you are armed with all of the information that you need in order. Oh, shoot. I went off screen a little bit. I'm sorry, you guys. Let me scroll to the side, make sure you can see it. Give you a second to get that note down. Now you know how to draw more complex Lewis structures, which are going to lead us to more complicated and interesting geometries. This page of notes is going to be really important for those of you that are considering going on to AP Chemistry next year, as our geometries and Lewis structures will be more complex. All right, good job. See you in class.